Tonight, we're going to look at the most familiar star in the universe from the inside out. The Sun is a sphere of plasma nearly 1.39 million kilometers across, suspended above Earth by distance and by habit. From here, it appears as a disk, a bright circle with no visible seam. Yet the disk is only the thin skin of a layered engine. Beneath it are regions where matter is compressed beyond anything found naturally on our planet, where light takes a long and indirect route, and where magnetic fields twist through electrically charged gas. The Sun has no floor, no shell you could tap, and no single moment when gas becomes rock. Its layers are changes in density, temperature, and the way energy moves. We will travel inward to the core, where hydrogen nuclei become helium. We will follow the energy through the radiative zone, where a photon can spend thousands of human lifetimes changing direction. We will rise through the convection zone, watch the visible photosphere form a moving boundary, and then continue into the chromosphere, the narrow transition region, and the immense corona. But how can a star have a surface that is not solid, an atmosphere hotter than the surface below it, and an interior that sends us evidence from particles made in the central furnace? By the end of tonight, you're going to understand exactly how each layer is defined, how energy moves between the layers, and how scientists can reconstruct a place no spacecraft can enter. Before we get started, if you love exploring the Sun as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Start with a number that gives the whole journey its scale. The Sun's diameter is about 1.39 million kilometers. If you placed Earth at its center and kept the proportions, more than 100 Earths could be lined across that distance. The number is not a wall to cross. It is a depth to imagine, a stack of physical conditions arranged by gravity. Every layer is connected to the next. The core powers the light. The light changes as it travels. The changing energy makes plasma rise and fall. That motion shapes magnetic fields. The fields reach through the atmosphere and carry the Sun's influence far beyond the visible edge. We will keep asking the same quiet question at every depth. What is happening here, and how does it prepare the next layer? Segment 2. A star made of depth. The first problem is the word inside. On Earth, inside usually means a room, a cavity, or a solid you can cut open. In the Sun, inside means a region where the pressure and density have different values, and where the dominant way of moving energy changes. The boundaries are useful models, not doors. Plasma crosses them. Heat diffuses across them. Magnetic fields ignore the clean lines we draw on a diagram. The Sun is a star of ordinary ingredients arranged in an extraordinary scale. Hydrogen and helium account for almost all of its mass, with small amounts of heavier elements mixed through the plasma. Gravity pulls every particle toward the center. Pressure pushes outward. The star exists in a long balance between those two tendencies, a condition called hydrostatic equilibrium. It is not motionless. It is balanced motion, held in a shape for billions of years. At the center, the weight of all the material above creates pressure. Move outward and the weight above you decreases, so pressure falls. Temperature follows a similar pattern through most of the interior, with the central region hottest. Density changes too. A teaspoon of core material, if it could be carried away without changing form, would weigh roughly as much as a small truck. That comparison is imperfect because the material would expand immediately, but it gives the direction of the difference. The Sun's radius is about 696,000 kilometers. We call the outer visible layer the photosphere, but the photosphere is only a few hundred kilometers thick in the vertical sense. Everything below it is hidden by the opacity of the plasma. We do not see a solid body through a clear atmosphere. We see the level from which most visible photons finally escape. That distinction will matter later. A star can look like a sharp-edged circle, even when its material thins gradually. The edge is created by the changing ability of light to travel, not by a crust. At the center, photons collide constantly. Near the edge, they can leave. The visible surface is therefore an optical surface, defined by the behavior of light. The 6 major regions we will use are the core, radiative zone, convection zone, photosphere, chromosphere, and corona. Some descriptions separate the narrow transition region between the chromosphere and corona. We will give it its own stop because the temperature change there is one of the sun's clearest puzzles. Pressure plasma and the meaning of hot. The next layer inward is not reached by drilling. It is reached by changing the conditions in your model. Imagine moving downward through a transparent mathematical sphere. The gas becomes denser, collisions become more frequent, and the pressure rises. At the same time, the atoms are stripped of electrons. The result is plasma, an electrically charged state in which nuclei and electrons move through one another rather than staying in ordinary atoms. Plasma is not simply a hotter version of air. Its electrical behavior lets magnetic fields guide it, store energy in it, and release that energy suddenly. The sun's visible motions are therefore fluid motions and electromagnetic motions at once. A rising parcel of plasma carries heat. A loop of magnetic field can hold a prominence above the photosphere. A reconnection event can turn stored field energy into radiation and fast particles. Temperature in the sun measures the average kinetic energy of particles. Density tells us how much material is packed into a volume. Pressure combines both ideas. At the core, all three are large. In the corona, the temperature is high, but the density is extremely low, so a spacecraft can pass through it without being instantly stopped by collisions. The heat is real, but it is spread through a very thin gas. The familiar phrase surface temperature can also mislead. The photosphere is about 5,500 degrees Celsius near the visible layer. The core reaches about 15 million degrees Celsius. Farther out, the corona can reach roughly 2 million degrees Celsius, hotter than the photosphere despite being farther from the furnace. The sun is not a simple hot center, fading smoothly toward cold space. This is why layer by layer is the useful way to approach it. Each region changes the rules for transport. In one region, energy travels mostly as radiation. In another, the material itself carries heat upward. At the boundary, we see light. Above it, magnetic fields and rare plasma form an atmosphere that has no crisp top. There is also a time hidden in the layers. The sunlight that reaches your window left the photosphere about 8 minutes and 20 seconds ago, but the energy that became that photon began its outward history much earlier. The final leap to space is quick. The preparation is ancient. #segment 4. The first problem is the most obvious one: power. At roughly the central quarter of the sun's radius, the density and temperature are high enough for sustained nuclear fusion. This core is not a separate ball with a shell around it. It is the region where pressure and temperature make the proton-proton chain efficient enough to supply the star's luminosity. The core reaches about 15 million degrees Celsius, or roughly 27 million degrees Fahrenheit. That number describes a gas in which nuclei move rapidly, but motion alone does not guarantee fusion. Two positively charged protons repel one another. They must approach closely enough for the strong nuclear force to act, and quantum tunneling gives a small fraction of collisions a path through the electrical barrier. When two protons meet through the first step of the chain, one changes into a neutron. The pair becomes a deuterium nucleus. A positron and a neutrino are released. Later, steps build helium-3, and two helium-3 nuclei can combine into helium-4 while returning two protons to the pool. The full chain turns four hydrogen nuclei into one helium nucleus with a little mass becoming energy. The reaction is slow by design. A proton in the core is not consumed in a single explosive instant. The sun's moderate mass keeps its fusion rate steady over billions of years. If the rate rose sharply, the core would expand and cool, reducing the reaction. If the rate fell, gravity would compress the core and raise the temperature. The star contains a natural feedback loop. The core is about 86,000 miles, or 138,000 kilometers, thick in NASA's educational descriptions. Even there, the word thick is a distance, not an edge. Fusion becomes less common gradually outward as the temperature drops. The active core fades into a surrounding region where energy is still produced in smaller amounts, and then into the radiative zone, where energy is transported rather than generated. Every second, the sun converts roughly 600 million tons of hydrogen into helium, while about 4 million tons of mass become energy. The exact rate varies in explanatory models, but the essential scale is stable. A vast amount of material yields a small fraction of its mass as light. The sun can do this because it is vast. Hashtag Shaksha segment 5. The quiet chain reaction. Assume the core is assembled. The next question is how a reaction that begins with individual protons becomes a star-wide source of light. Fusion products do not shoot straight outward like sparks from a fire. They share energy with the dense plasma around them. Photons are created, absorbed, scattered, and re-emitted. Neutrinos take a different path. Neutrinos interact so weakly that most pass out of the sun almost immediately. A detector on Earth can register them as a direct message from the core, a stream that crossed the star without the long delay imposed on light. The first neutrino experiments found fewer particles than early calculations predicted, a puzzle later resolved through the discovery that neutrinos change flavor as they travel. Photons are more patient. In the central plasma, a photon may travel only a tiny distance before meeting an electron or another charged particle. It changes direction. Its wavelength changes. The original photon is absorbed and another is emitted. The energy moves outward, but no individual visible photon makes the whole journey from the core to the surface. This separation of messengers lets us compare two clocks. Neutrinos carry information from the present core to Earth in about 8 minutes and 20 seconds, the same travel time as other particles moving close to light speed. Photons carry energy through the interior by a random walk that NASA estimates at roughly 170,000 years to cross the radiative zone alone. The core's fusion also changes its composition. Hydrogen becomes helium, so the center slowly grows richer in helium and denser in the products of its own work. The sun is not chemically identical at every radius. Its age is written as a gradient, with the deepest material having experienced the most fusion. That gradient affects the star's future. As hydrogen is used, the core contracts slightly and heats. The surrounding layers respond. The sun's brightness rises slowly over geological time, not because the star is running out of fuel today, but because its internal balance changes as the fuel is rearranged. There is no flame in the core. Combustion is a chemical process involving electron shells. Fusion changes atomic nuclei. Calling the center a furnace is a useful image only if we remember that its fuel is nuclei, its ash is helium, and its heat is held by gravity. Hashtag segment 6, a teaspoon of the center. The first anchor number is density. Near the solar core, the average density is about 150 grams per cubic centimeter. Gold is about 19.3 grams per cubic centimeter. Lead is about 11.3. Core material is not a solid ingot, but the comparison shows how gravity compresses plasma when an entire star presses down from every direction. At this depth, pressure is enormous because pressure is the weight of all the layers above, distributed through a fluid. A particle near the center is surrounded by other particles in every direction. There is no down in the ordinary human sense, only a net pull toward the center that becomes smaller exactly at the center and stronger as you move outward through the interior. The core's density does not mean its particles are packed like marbles. The plasma is hot and electrically charged. Nuclei occupy a small fraction of the volume, while electrons move through the same space. Yet the distance between particles is short enough and collisions frequent enough that radiation cannot travel far without interacting. One consequence is opacity. Opacity is the difficulty radiation has in moving through matter. In the core, high opacity makes the photon random walk extremely slow. Farther out, as density falls and the composition changes, opacity shifts. The sun's internal transport is therefore a conversation between temperature, density, and the cross-sections of atoms and ions. Another consequence is pressure support. The core would collapse if the gas pressure and radiation pressure did not balance gravity. Fusion maintains the temperature that maintains the pressure. This is why a star can be stable without being rigid. Its shape is a continuous solution to equations of gravity and fluid motion. The core also creates the sound of the sun in a metaphorical but measurable sense. Pressure waves travel through the plasma. They reflect from changing density and temperature. The surface rises and falls by tiny amounts as those waves pass. Scientists use the oscillations to infer the interior, much as a physician uses sound waves to see structures hidden beneath skin. The sun is therefore both opaque and transparent, depending on the messenger. Light from the core is transformed and delayed. Neutrinos pass through. Pressure waves leave patterns at the surface. Each channel reveals a different layer. Hashtag segment 7. The first outward step. The next layer is not empty space around the core. It is a broad region of hot plasma in which fusion becomes rare and radiation becomes the main carrier of energy. We call it the radiative zone. Its name describes transport, not a special material. Photons still collide, but the plasma itself does not rise in large overturning cells through most of the zone. Energy leaves the fusion region as electromagnetic radiation, but the spectrum is not the warm, visible light we associate with the sun. Deep inside, the photons are energetic, often in X-ray and gamma-ray ranges. Each interaction changes their direction, and usually their energy. By the time energy reaches the photosphere, it has been redistributed into a spectrum with much of its power in visible and infrared wavelengths. Imagine a crowded corridor where every traveler takes one step, bumps into someone, and starts in a new direction. The crowd slowly advances, but no traveler keeps a straight route. In the radiative zone, energy does something similar. The net flow is outward, even though the local paths are tangled. The outward temperature gradient is steep enough to transport energy by radiation. A small rise in temperature changes the intensity of the local radiation field. The mathematical condition for stability depends on how quickly temperature falls with radius and on how opaque the material is. If the gradient becomes too steep, radiation alone cannot carry the load. That is where convection begins. The radiative zone reaches from the outer core to roughly 70% of the sun's radius, though the exact boundary is a model inferred from observations. Its extent makes it one of the largest regions in the star. A ray of energy can spend a time comparable to the age of many human civilizations simply working its way across. During this long passage, energy loses the memory of the exact fusion event that created it. The sun's surface does not show a snapshot of a proton reaction. It shows the sum of innumerable interactions, averaged by matter and by time. The light is new at the surface, but its energy is ancient. That distinction protects the sun from sudden changes. The core can fluctuate locally, while the radiative zone smooths the output. The star has a thermal buffer. It stores energy in matter, temperature gradients, and the long delay of photon transport. Hashtag Sortie Segment 8. A journey of 170,000 years. NASA estimates that energy takes about 170,000 years to cross the radiative zone. The number is a useful anchor, but it is not the age of a particular photon. Photons are absorbed and re-emitted so often that the identity of a single particle is lost. The estimate describes the time required for energy to diffuse outward through the region. Place that duration beside human history. 17,000 decades ago, no city existed in the form we would recognize. 17,000 decades before a present-day message, people were learning to shape stone and follow herds. The sun's light does not hurry from the core. It accumulates a long interior history before the last few minutes of its trip through space. In a random walk, the average distance grows with the square root of the number of steps, not in a straight line. That is why adding millions of collisions can produce only a slow net displacement. The radiative zone is a vast three-dimensional random walk with a steady bias outward because the core is hotter than the layers above it. The plasma's opacity is shaped by the interaction of photons with electrons and ions. At some energies, an ion can absorb a photon efficiently. At others, scattering dominates. As the photon energy changes, the preferred interaction changes too. Energy is repeatedly converted between radiation and the thermal motion of matter. The zone is not a dark cavern. It glows internally, but the glow is trapped. A camera placed there would not see to the next meter because light would scatter almost immediately. The darkness of the interior is therefore an optical fact, not an absence of radiation. At the outer edge, the temperature has fallen enough for convection to become more efficient. The radiative gradient reaches a point where a parcel of plasma that rises a little remains warmer and less dense than its surroundings. Buoyancy takes over. The transition is not a sudden hole opening in the star. It is a change in the dominant transport method, a slow handoff from photons to moving matter. The energy has not reached the surface yet. It has only reached the region where the sun's material begins to carry it as a visible motion. Hashtag Segment 9. Opacity, wavelengths, and the hidden map. Assume the radiative zone is a library with shelves that rearrange themselves. Each shelf is an atomic transition, a route by which matter can absorb or emit a photon. The library is denser near the core and more open outward. The path an energy packet takes depends on which shelves are available at that depth. Opacity determines how a star transports energy and how its brightness changes with time. In the sun, Heavy elements contribute strongly to opacity, even though hydrogen and helium dominate the mass. Small concentrations of carbon, oxygen, iron, and other elements provide many absorption lines. Their influence reaches beyond their percentage on a scale. The term heavy element has a special meaning in astronomy. It means any element heavier than helium. A star can be mostly hydrogen and helium while still carrying a chemical signature from earlier generations of stars. The Sun formed from a cloud enriched by ancient stellar history. Its interior is a record of that inheritance. As radiation climbs outward, it moves through material with changing ionization states. Electrons are bound at one depth and stripped at another. Each change alters the way light interacts with matter. The radiative zone is therefore not a uniform fog. It is a stratified plasma whose opacity profile helps set the shape of the star. The Sun's mass and composition place it on a particular path among stars. A more massive star would have a different core temperature, different fusion reactions, and a shorter life. A smaller red dwarf would mix its interior more thoroughly and burn fuel more slowly. The layers we are studying are specific to a star of the Sun's size. Radiation also carries angular momentum. The Sun rotates, but it does not rotate as one rigid body. Different depths and latitudes move at different rates. The radiative interior rotates more nearly as a unit, while the outer convection zone shows stronger differential rotation. Somewhere between them, a thin shear layer stores the conditions for magnetic field generation. That shear layer is the Tachocline. It is not one of the 6 broad layers visible in a simple diagram, but it is a crucial interface. A difference in rotation can stretch magnetic fields like taffy. The fields then rise, emerge, and shape the surface features we see from Earth. Hashtag Hutter Segment 10. The Tachocline, a boundary that moves. The first problem is the most subtle one, rotation. The Sun's equator completes a turn in roughly 25 days, while regions closer to the poles take longer. This differential rotation is measured at the surface, but its origin is rooted deeper. The radiative interior rotates more uniformly, and the Tachocline sits where the two patterns meet. A shear layer is a place where neighboring flows slide past one another. In the Sun, the shear is not a thin crack. It is a broad zone whose exact shape is inferred from helioseismic measurements. The movement winds magnetic field lines around the star. The field stores energy and changes the conditions for plasma motion. The magnetic field is generated by a dynamo, a feedback involving rotation, convection, and electrically conducting plasma. The details are active research, but the broad pattern is clear. Motion creates fields. Fields influence motion. The cycle repeats, reversing the Sun's large-scale magnetic polarity about every 11 years. Sunspots are the visible footprints of concentrated magnetic fields. They look dark because they are cooler than the surrounding photosphere, not because they are holes. Their temperature is still thousands of degrees Celsius. A strong field suppresses some of the upward convection that normally brings heat to the surface, leaving a darker patch against the brighter surrounding plasma. The Tachocline helps explain why sunspots appear in bands that migrate with the solar cycle. It is a reservoir for field organization, while the convection zone above it churns and transports the field upward. Surface activity is therefore connected to a layer we cannot see directly. A boundary in a star is never only a line. It is a place where one behavior hands over to another. The Tachocline hands rotation differences to magnetic structure. The radiative zone hands diffusing energy to the convective zone. The next layer will carry that energy with moving plasma. The sun's interior has now brought energy from the core to about 70% of the radius. The remaining path to the visible surface is shorter in distance, but more visibly active. #Shacktag segment 11. The convection zone begins. The next layer is the convection zone, the outer roughly 30% of the sun's radius. Here, the plasma itself carries most of the energy. Hot material rises from deeper levels, spreads beneath the photosphere, cools, and sinks again. The cycle resembles a slow planetary weather system, except each cell can be larger than a continent and the fluid is electrically charged. Convection begins when radiation cannot carry the outward energy efficiently enough without creating an unstable temperature gradient. A parcel that rises expands and cools, but it can remain warmer than its surroundings. Its lower density gives it buoyancy. It continues upward until it has surrendered enough heat to become denser and sink. The zone is not a single overturning wheel. It contains cells nested within cells, with immense broad flows below and smaller granules near the surface. The deeper cells can span tens of thousands of kilometers. The near-surface cells are smaller and faster, forming the textured patterns seen in detailed solar images. Because the sun is plasma, convection also moves electrical currents. Those currents generate and reshape magnetic fields. The heat transport and the magnetic dynamo are therefore linked. A change in one can affect the other, and the surface records the result as spots, bright regions, filaments, and eruptions. The temperature falls through the convection zone from millions of degrees near its base to several thousand degrees near the top. The matter remains ionized through much of the region, but the balance of ions and electrons changes with depth. Near the photosphere, hydrogen begins to recombine in places, altering opacity and making the visible boundary sharper. The convective flow is slow compared with light. A rising bubble may take days to reach the surface. The magnetic field can persist for months or years. The sun can therefore look calm from minute to minute, while its deep transport continues on longer clocks. At the top of the convection zone, energy has become a pattern of motion. A few hundred kilometers farther out, that motion will be painted into light. #segment 12. Granules, cells, and the moving surface. The first problem is scale. The sun's granules are small compared with the star, but enormous compared with earthly weather. Each bright granule is a rising column of hot plasma. Dark lanes mark cooler material sinking back down. Individual granules can be about 1,000 kilometers across and last only minutes before changing shape. A high-resolution image of the photosphere looks like a field of pale grains because the convection cells are close to the layer from which light escapes. The pattern is not a painted texture. It is the visible signature of heat moving through the top of the convection zone. Supergranules sit above a larger scale. They can span tens of thousands of kilometers and persist for a day or two. Their horizontal flows gather magnetic fields into the borders between cells. Those borders become channels where bright network structures and small eruptions are more likely to appear. The cells do not rise as solid bubbles. Plasma expands, changes density, radiates, and mixes with its neighbors. The language of rising and sinking is a shorthand for a fluid field. Each parcel is part of a continuous circulation, like water in a pot but stretched over a star. The visible pattern also tells us where the star is opaque. We see the top of a convective column only when photons can escape. Deeper down, light is scattered before it can travel far. The granule is therefore a window into the upper convection zone, not a photograph of the entire cell. A surface that changes every few minutes can still be stable on a stellar timescale. The average brightness of the sun varies only slightly over a solar cycle, even though individual cells appear and vanish constantly. Stability is found in the statistics of countless motions, not in the stillness of any one patch. The sun's outer interior is now close enough to the edge that the word surface becomes useful, but only as a visual convention. The next layer is where the majority of visible sunlight escapes. Hashtag Schachter segment 13, the photosphere, an optical surface. The next layer is the photosphere, the sphere of light. It is about 400 kilometers, or 250 miles, thick in NASA's descriptions. That is tiny compared with the sun's radius of roughly 696,000 kilometers. The disk appears sharp because opacity changes rapidly through this layer, allowing photons to leave over a narrow range of depths. The photosphere is not solid. There is no place where a foot could stand, only plasma becoming thin enough for light to escape. The temperature at the visible level is around 5,500 degrees Celsius, or about 10,000 degrees Fahrenheit. Even carbon, in forms such as graphite, would not remain a solid there. Most of the sun's radiant energy leaves through the photosphere. The spectrum resembles a thermal continuum with dark absorption lines superimposed. Those lines are fingerprints of elements in the cooler gas above and within the visible layer. By measuring them, astronomers learn what the sun contains without collecting a sample. The photosphere has a temperature gradient. The deepest visible portions are hotter than the upper portions. At the center of the solar disk, we see slightly deeper and therefore hotter layers. Near the limb, our line of sight passes through the upper, cooler parts for a longer distance. The edge looks darker, a property called limb darkening. A photon emerging from the photosphere is not necessarily brand new. It may have been absorbed and re-emitted many times in the interior. What is new is its freedom to travel outward. Once beyond the optical depth of the photosphere, it can cross the 150 million kilometers to Earth in a little over 8 minutes. The photosphere also marks the lower boundary of the sun's atmosphere. Above it, density drops rapidly. The plasma is still connected to the interior by magnetic fields and by waves, but its behavior becomes more rarefied. The next layer will be visible only under special conditions or through carefully chosen wavelengths. The surface is therefore a measurement layer, not a material shell. It is where the star becomes transparent enough for us to see. Hashtag segment 14. Seeing depth, not a wall. Assume the photosphere is a window. The view through a window depends on the glass, the angle, and the light behind it. The sun's view depends on the opacity, wavelength, and geometry. Different wavelengths reveal different heights. Ultraviolet light, visible light, and X-rays trace different temperatures and densities. The photosphere's granules are brightest in their centers because hot plasma rises there. As that plasma spreads and cools, the edges become darker. The pattern changes on a timescale of minutes. A long exposure would smooth it into a modeled average, while a rapid sequence reveals the flow. The photosphere also contains pores, faculae, and sunspots. Faculae are bright magnetic features that can remain visible near the limb, where their geometry lets hot walls rise above darker surroundings. Pores are smaller dark concentrations of magnetic field. Sunspots are larger and often organized into pairs or groups. The magnetic field changes the local pressure and the path of convection. A strong vertical field can suppress the upward motion of plasma, cooling the region. A horizontal field can connect distant patches. The surface appearance is the result of the field's three-dimensional geometry projected onto a two-dimensional disk. Helioseismology makes the photosphere a listening surface. Pressure waves travel through the interior and alter the timing of tiny surface motions. By mapping those changes, scientists infer flows beneath regions that look quiet. The same surface that emits sunlight also carries vibrations from the hidden interior. The apparent disk is thus a composite. It contains the top of convective cells, the footprints of magnetic fields, and the optical depth at which photons escape. When we say we are looking at the sun, we are looking at a particular layer chosen by our instrument and by the atmosphere between us. The next layer will be visible as a reddish rim during a total solar eclipse and as a bright structure in the hydrogen alpha line. Hashtag segment 15, Sunspots and the 11-year rhythm. The first anchor number is the approximately 11-year solar cycle. Sunspot numbers rise and fall over that period as the sun's magnetic field reorganizes. The cycle is not a metronome with perfect spacing, but it is persistent enough to shape calendars of solar activity. A sunspot appears dark because its magnetic field inhibits some convective heat transport. Its temperature is still thousands of degrees Celsius, but the surrounding photosphere is brighter and hotter. The spot is a contrast effect, a cool island in a luminous sea. Sunspots often arrive in groups with opposite magnetic polarities. Their orientation reverses from one cycle to the next. After roughly 11 years, the number of spots returns toward a minimum, but the global field has completed a 22-year magnetic cycle in which its polarity returns to its original direction. The fields that make sunspots emerge from deeper layers. A bundle of magnetic flux can become buoyant, rising through the convection zone. Where it breaks through the photosphere, it forms two footprints connected by an arching field above the surface. The visible pair is one end of a structure that extends into the atmosphere. Bright plages surround many spots in the chromosphere. Their energy comes from magnetic fields concentrating and dissipating above the photosphere. The same field can produce a stable dark spot over days and then release energy in a flare over minutes. The cycle changes the sun's ultraviolet output, particle environment, and magnetic structure. The total visible brightness changes by only about 0.1% across a typical cycle, yet the space environment can change far more strongly. A small adjustment in total light can accompany a large reconfiguration of magnetic fields. Sunspots were recorded by Galileo and earlier observers, but modern telescopes measure their magnetic fields directly through the Zeeman effect, a splitting of spectral lines. The spectrum becomes a map of field strength and direction. The photosphere is not only a light source, it is the place where the hidden dynamo writes its signature. Hashtag segment 16, flares and magnetic reconnection. The next question is what happens when magnetic fields cannot remain in the shape imposed by the moving plasma? In a flare, field lines rearrange through magnetic reconnection. Energy stored in the field is converted into heat, radiation, and streams of energetic particles. The visible flash is one part of a process that spans the photosphere, chromosphere, and corona. A flare can brighten the sun in X-rays and ultraviolet light within minutes. The energy release is concentrated, but the source region may cover an area larger than Earth. The event is not an explosion of the whole star. It is a sudden change in one magnetic system. Reconnection works because the plasma is an excellent conductor on large scales, but not perfectly so in thin current sheets. Field lines that were effectively frozen into the moving plasma can break and join a new arrangement. The change releases tension, like a stretched elastic band snapping into a shorter path. The particles accelerated in a flare can travel along magnetic field lines. Some strike the lower atmosphere, heating it and producing bright ribbons in ultraviolet light. Others escape into interplanetary space. The flare's effects therefore appear at multiple heights and in multiple wavelengths. Not every flare produces a coronal mass ejection. A CME is a much larger expulsion of magnetized plasma. A flare is a burst of energy. A CME is a moving cloud of material and field. They can occur together, but they are distinct phenomena. The energy in a large flare can be comparable to billions of megatons of TNT, but comparisons to terrestrial explosions can obscure the physics. The important feature is not a number chosen for drama. It is the coupling of magnetic fields, plasma, and the space between planets. The sun's magnetic field stores the history of the convection zone. A twist introduced deep below can emerge days or weeks later as an active region. The surface is a delayed report from the interior. Above the flaring region, the chromosphere glows in the next layer of the journey, #segment 17. Prominences held in the sky. A prominence is cooler, denser solar material suspended above the photosphere by magnetic fields. Seen against the dark sky beyond the limb, it can look like a looping red arch. Seen against the bright disk, the same structure becomes a dark filament. The difference is the background, not the object. The plasma in a prominence is cooler than the surrounding corona, sometimes around 10,000 Kelvin rather than millions. It remains suspended because magnetic field lines form a cradle. Gravity pulls downward. Magnetic tension and pressure support the material above the surface. Prominences can remain stable for days or weeks. Their stability does not mean the field is still. Small motions ripple through the structure. As the magnetic configuration changes, the prominence can erupt and become part of a coronal mass ejection. The chromosphere and corona are therefore connected by vertical structures. Spicules shoot upward for a few minutes. Prominences can arch for weeks. Flare loops heat in minutes and cool over hours. The atmosphere has many clocks operating at once. The word atmosphere suggests air, but the solar atmosphere is plasma whose density drops rapidly with height. Sound waves can travel through it, while magnetic waves carry energy along field lines. The color and shape we see depend on which atoms are excited and which wavelengths our instrument selects. During a total eclipse, the moon blocks the bright photosphere and the chromosphere appears as a thin pink rim. Prominences may protrude like small rose-colored flames. The corona spreads beyond them in pale streamers, revealing that the sun's atmosphere is much larger than the visible disk. Nothing is burning in these arcs. Their color comes from atomic emission, especially hydrogen. The magnetic field supplies the architecture. The plasma supplies the light. The chromosphere is the middle atmosphere, a narrow layer whose temperature rises with altitude in a way that seems backward if we imagine a simple fire. #segment 18. The chromosphere. The next layer is the chromosphere, extending roughly 400 to 2,100 kilometers above the photosphere. Its name means color sphere, a reference to the reddish light seen during an eclipse. It is thin compared with the sun's 696,000 kilometer radius, yet it hosts waves, jets, filaments, and the lower roots of the corona. Near its base, the chromosphere can be around 4,000 Kelvin. Higher up, the temperature rises toward about 8,000 Kelvin. This upward increase begins before the dramatic jump of the transition region. The cause involves magnetic and acoustic energy moving upward from the convective interior. The density falls rapidly through the layer. Collisions become less frequent, and atoms can emit photons that escape in distinctive spectral lines. Hydrogen alpha is especially useful because it traces the chromosphere's structure in a deep red wavelength. Other instruments use ultraviolet lines from ions formed at different temperatures. Spicules are narrow jets that rise from the chromosphere and fade after minutes. They may reach thousands of kilometers above the photosphere. In a high-resolution image, the limb can look like a field of fine grass, each blade a brief upward motion of plasma. The chromosphere is also where magnetic fields guide much of the atmosphere's movement. Loops rooted in opposite polarity regions rise through it. Small-scale reconnection can launch jets. Waves traveling along field lines deposit energy at higher altitudes. The layer's brightness changes with wavelength. In visible light during ordinary conditions, the photosphere overwhelms it. In hydrogen alpha and ultraviolet light, the chromosphere becomes a textured world. Looking at the sun therefore means choosing a window, and each window has its own altitude. At the top of the chromosphere, a narrow transition region changes the temperature by hundreds of thousands of degrees over roughly 100 kilometers. The sun does not warm smoothly there. It turns upward sharply. Hashtag segment 19. Spicules and spectral fingerprints. The first problem is how a thin atmosphere can carry energy upward without simply dispersing into space. Magnetic fields provide channels. They do not act as solid pipes, but charged particles spiral and flow along field lines. Waves can travel along the same geometry, carrying energy from the lower atmosphere toward the corona. Spicules are one visible result. They are short-lived, narrow jets that rise and fall or fade as the plasma changes state. Their exact role in heating the corona remains an active area of research. Some populations may carry mass and energy upward, while others may dissipate lower down. Spectroscopy turns color into measurement. Each element has allowed transitions between energy levels. When electrons move between those levels, atoms emit or absorb photons at specific wavelengths. A line's brightness, width, and shift reveal temperature, density, turbulence, and motion along our line of sight. A spectral line can be shifted by the Doppler effect. If plasma rises toward a telescope, the line moves slightly toward shorter wavelengths. If it falls away, the line shifts longer. The motions are small, but modern instruments can measure them across the disk, building a velocity map of the atmosphere. The chromosphere also shows fibrils, threads aligned with magnetic fields. In quiet regions, they create fine patterns. Near active regions, they crowd around loops and brighten in response to flares. A magnetic map and a hydrogen alpha image together reveal a three-dimensional structure projected onto a flat detector. The layer is a threshold. Below it, density and collisions keep matter closer to fluid behavior. Above it, the plasma becomes thin enough that individual particle motions and magnetic waves dominate. The same field can look like a broad flow below and a narrow strand above. Solar observatories often combine several instruments rather than relying on one perfect photograph. The Solar Dynamics Observatory, launched in 2010, monitors the sun in multiple ultraviolet wavelengths and tracks magnetic activity continuously. The result is a time series, not a single portrait. The chromosphere gives way to a region so thin that it is measured in tens of miles, yet its temperature climbs toward 500,000 Kelvin. Hashtag segment 20. The narrow transition region. The next layer is the transition region, a thin and irregular band between the chromosphere and corona. NASA descriptions place it at about 100 kilometers thick, roughly 60 miles, though its shape varies with magnetic structure and time. In that short distance, temperature rises from around 8,000 Kelvin to hundreds of thousands of Kelvin. The transition is not a flat shell. It folds around loops, curtains, and jets. Some portions rise high above the photosphere. Others dip close to it. Its thinness is a statement about temperature gradient, not a physical membrane. At these temperatures, atoms lose more electrons. The ions visible in ultraviolet lines change rapidly with height. A line that indicates 50,000 Kelvin may form below 1, indicating 500,000 Kelvin, letting scientists arrange an atmosphere that no camera can see directly. The region is also a bottleneck for energy. Conductive heat from the hot corona moves downward along magnetic field lines. Radiative losses carry energy away in ultraviolet light. The transition layer balances upward heating, downward conduction, and radiation into space. The steep gradient is one reason the corona can be hotter than the photosphere. Heat is not traveling only by the simple rule that warmer material sits below cooler material. Magnetic waves and reconnection deposit energy in the thin upper atmosphere, while the lower atmosphere radiates efficiently. The transition region can brighten during flares. As loops heat, the layer shifts and the spectral lines change. A flare is therefore visible not only as a flash, but as a moving temperature boundary. Crossing this layer, we leave the dense atmosphere behind. The corona begins, a vast, sparse envelope held by magnetic fields and gravity with temperatures near millions of degrees. Hashtag Segment 21, the corona and the heating mystery. The first problem is the corona's temperature. The photosphere below it is around 5,500 degrees Celsius, yet the corona reaches roughly 2 million degrees Celsius in its hottest regions. A simple furnace should weaken with distance. The sun's atmosphere does not follow that simple pattern. The corona is the outer atmosphere of the sun, but its boundary is not a shell. It thins into the solar wind, a flow of charged particles that fills interplanetary space. Magnetic loops can hold dense patches close to the sun, while open field lines let plasma stream outward. At coronal temperatures, atoms lose many or all of their electrons. The gas becomes extraordinarily thin. A cubic centimeter may contain far fewer particles than the same volume near the photosphere, so the corona can be hotter without carrying the same total heat as a dense room-sized sample. Temperature is an average particle energy, not a measure of how much matter is present. The heating source is connected to magnetic fields. Convection below the photosphere continually braids and shakes those fields. Waves can travel upward along them, and small reconnection events can release stored energy. Researchers study how much each process contributes, because the corona is not heated by one uniform mechanism everywhere. The corona's light is mostly invisible to human eyes. Extreme ultraviolet and X-ray instruments reveal its hottest structures. During a total solar eclipse, scattered sunlight from the corona becomes visible as a pale halo. The shape of that halo follows the magnetic architecture of the moment. Coronal loops trace closed magnetic fields. Hot plasma follows their arches, making luminous strands that can last from minutes to hours. A loop is not a rigid tube. It is a volume where particles are guided along field lines, with density and temperature changing from one foot point to the other. The heating puzzle is therefore a transport puzzle. Energy begins in moving plasma, enters magnetic fields and waves, and appears as high particle energies far above the visible surface. The missing steps are narrow, dynamic, and difficult to measure from a distance. Parker's solar probe was designed to enter that problem directly. Its instruments sample fields and particles close to the sun, where the corona is still structured rather than mixed into the broad solar wind. The mission turns a distant atmosphere into a nearby laboratory. The corona also teaches a careful lesson about the word heat. A thermometer placed in a thin gas would register high particle energies, but an object moving through that gas would not receive the same heat load it would receive in a dense oven. Collisions are too infrequent to transfer energy efficiently. The strongest thermal danger near the sun comes from intense radiation, while the corona's temperature describes the speed of the particles that happen to be there. Magnetic fields make the distinction visible. A loop can contain a small amount of very hot plasma, shining in extreme ultraviolet light because its ions are in particular charged states. A neighboring open field can carry a faster wind while looking darker. Brightness, temperature, and density are related, but they are not interchangeable. A map of one is never a complete map of the others. This is why coronal heating remains a problem, rather than a missing fact in a textbook. Instruments can measure waves, particle distributions, and field changes, yet the smallest scales where energy dissipates are difficult to resolve. The corona is a place where enormous structures are built from tiny processes. Assume the corona is a map of magnetic field lines. The next question is why some regions appear dark in extreme ultraviolet images. Coronal holes are areas where field lines open outward, allowing plasma to escape more freely. They look dark because their density is lower and their characteristic temperatures differ from the surrounding loops. A coronal hole is not an empty hole in the sun. It is a region of thin magnetized plasma. Open field lines extend away from the surface and carry a faster solar wind. When a hole faces Earth, its stream can sweep past our planet for days as the sun rotates. Between open regions, closed loops gather into streamers. Streamers are bright because they hold more plasma along curved fields. They stretch outward above the visible limb and often become the largest shapes in an eclipse photograph. Their bases can change as active regions emerge and decay. The corona rotates with the sun, but not as a solid shell. Magnetic structures move across the disk, and the pattern we see depends on latitude, depth, and whether a field line is open or closed. A streamer observed today may have a different shape when the same longitude returns. The low density changes how energy travels. Along a strong field, thermal conduction can carry energy efficiently from a hot loop toward its foot points. Across the field, transport is much weaker. The corona is therefore a collection of connected lanes rather than a uniformly mixed atmosphere. Coronal holes and streamers also shape the solar wind before it reaches the planets. Fast streams from open fields can overtake slower streams from dense regions. Their interaction creates compressed boundaries that travel outward through the heliosphere. The outer atmosphere has no final edge. The density simply falls until the particles are better described as a wind than as a static corona. The transition from one name to the other is a change in flow, not a line painted in space. Seen from Earth, the corona seems delicate. In the physics of space weather, it is a moving boundary between the sun and everything around it. The next layer of our journey is the wind that carries that boundary outward. Streamers can be understood as reservoirs. Their closed fields hold plasma that would otherwise escape, and the material slowly leaks or is released when the magnetic arrangement changes. At the edge of a streamer, a thin current sheet can form, separating magnetic directions that point away from one another. Small changes in that sheet can send blobs of plasma outward. Coronal holes have their own texture. They contain bright points, tiny loops, and transient jets, even though the region looks dark in a broad image. Darkness means that the instrument receives less emission in its chosen wavelength. It does not mean that every temperature or every density is low. Changing the filter can reveal structures hidden inside the apparent void. The rotating sun carries these patterns across our view. A hole near the equator can return to a similar longitude after one rotation, while a high latitude feature changes its relation to the observer. The corona is a three-dimensional, time-dependent atmosphere viewed from one moving planet. The first problem is that the sun does not end at the photosphere. The solar wind is a continuous outflow of electrons, protons, and heavier ions from the corona. Near Earth, the particles arrive as a tenuous stream moving through the space between planets. The wind begins where coronal gravity can no longer hold every particle in place. Heating and pressure accelerate the plasma along open magnetic field lines. The flow becomes supersonic relative to the local plasma, creating a moving environment that fills the solar system. The sun's magnetic field travels with the wind. Because the sun rotates, the field lines trace a spiral through space, often called the Parker spiral. A particle released near the sun can therefore reach a distant planet along a path that curves with solar rotation rather than pointing straight outward. The combined field and plasma inflate a magnetic bubble called the heliosphere. Its shape is influenced by the sun's changing wind and by the interstellar medium surrounding the solar system. The bubble extends far beyond the orbit of Neptune, where sunlight is already weak and cold space dominates the scenery. Voyager 1 and Voyager 2 cross the heliopause, the outer boundary where the solar wind yields to interstellar plasma in the early 21st century. The boundary is not a solid wall. It is a region of changing particle populations and magnetic fields. Solar wind particles carry angular momentum away from the sun. The loss is small on a human timescale, but over billions of years, it contributes to the gradual slowing of the sun's rotation. The atmosphere is therefore also a break, connecting the star's surface to the space around it. The wind can be smooth, turbulent, fast, or slow. It contains waves, shocks, and magnetic structures that preserve traces of the corona where they formed. A spacecraft sampling the wind is reading a weathered version of the sun's atmosphere. Earth sits inside this bubble. Our magnetic field deflects most of the wind, while a small fraction enters through reconnection and funnels toward the polar atmosphere. The aurora is one visible sign that the solar interior and atmosphere remain connected to a planet 150 million kilometers away. The wind is not a uniform breeze. It carries parcels with different temperatures, densities, and magnetic directions. Waves travel through those parcels, and shocks form where a fast stream catches a slow one. At a spacecraft, the changes can look like a sequence of boundaries crossing the detector: a quiet interval, a compressed region, a rotation of the field, and then a return to ordinary flow. The heliosphere also filters some of the high-energy particles arriving from interstellar space. Its magnetic fields turn and scatter charged cosmic rays, creating a changing shield around the planets. The shield is not complete, and it is not rigid. It expands and contracts as the solar cycle alters the pressure of the wind. In this sense, the sun's atmosphere is an environment rather than a backdrop. Every planet moves through a version of it. The outer planets experience a thinner, weaker wind, but they still orbit inside the same magnetic bubble that began in the corona. The next question is how to measure a corona that begins millions of kilometers above the visible surface. Parker's solar probe carries instruments for fields, waves, particles, and imaging. On December 24th, 2024, it passed about 3.8 million miles above the sun's surface at roughly 430,000 miles per hour, a record close approach for a human-made object. Those figures describe the spacecraft's path, not a dive into the photosphere. Parker flies through the outer corona, protected by a carbon composite heat shield. The shield faces the sun while the instruments operate in its shadow, sampling a region where the sunlight is intense but the plasma remains extremely thin. At that distance, the spacecraft can measure magnetic fields before they have been smoothed by millions of kilometers of expansion. It can detect switchbacks, sudden reversals in the direction of the magnetic field that travel through the wind. Their origin may lie in the corona's turbulent lower layers. Parker also measures the speeds and energies of particles. Electrons and ions do not all move together. Some stream outward, some reflect from waves, and some gain energy in brief structures. Comparing those populations with images of the corona helps link a particle measurement to a source region. The mission's name honors Eugene Parker, whose work in the 1950s described the solar wind before it was directly observed. The theory predicted that a hot corona could not remain static and that an outward flow was inevitable. Spacecraft later found the wind moving through the planetary system. A close pass also changes the meaning of distance. 3.8 million miles sounds enormous from Earth, yet it is only a few solar radii above the surface. The spacecraft is still within the sun's magnetic neighborhood, where small structures can control the larger wind. The probe's heat shield does not make the environment gentle. It makes the exposure survivable. The surrounding plasma is hot but sparse, while the direct sunlight carries most of the thermal load. The distinction between particle temperature and radiant heating is essential to every mission near the sun. Each orbit adds another piece to the heating puzzle. Parker cannot watch one particle from the core to Earth, but it can sample the place where coronal fields become solar wind. The interior, the atmosphere, and interplanetary space become one continuous experiment. The spacecraft also shows why distance alone is a poor guide to danger. A region can be extremely hot yet thin, while a cooler region can deliver more energy because it contains more particles or more radiation. Parker's instruments separate those channels. They measure the field, the particle speed, the particle direction, and the waves that connect one measurement to the next. Its close passes are arranged through the gravitational influence of Venus. Each encounter changes the orbit, allowing the probe to approach the sun more closely while keeping its instruments pointed behind the shield. The flight is a long sequence of carefully timed adjustments, not a straight plunge. As the probe moves through the corona, it samples structures that change faster than a signal can cross the entire heliosphere. A switchback recorded for a few minutes may be the local trace of a process that began in a small magnetic region on the sun. The first anchor number is again the approximately 11-year solar activity cycle. The sun moves from a quiet minimum to a crowded maximum and back as sunspots, flares, and magnetic structures change in number and latitude. The cycle is a pattern in a living dynamo, not a schedule that predicts every event. At minimum, the visible disk may show few sunspots. The large-scale magnetic field is relatively simple, with open and closed regions arranged on broad scales. As activity rises, new flux emerges, spots multiply, and the corona becomes more complex. Solar maximum does not mean the sun is uniformly bright or uniformly dangerous. It means magnetic complexity and the likelihood of energetic events are elevated. A quiet day can occur inside a busy year, and a strong flare can emerge from one compact active region. Space weather begins with this changing magnetic environment. Flares send bursts of electromagnetic radiation. Coronal mass ejections launch clouds of magnetized plasma. High-speed streams leave coronal holes. Each disturbance travels differently and reaches the planets on a different timescale. Radiation from a flare arrives at Earth in about 8 minutes and 20 seconds because it travels at light speed. A CME takes longer, often measured in days, because it is a moving cloud of matter. The two signals can begin together but deliver their effects separately. When a CME reaches Earth's magnetic field, it can compress the magnetosphere and drive currents in the upper atmosphere and on the ground. Satellite operators, power grid engineers, and radio users monitor the sun because the same fields that make the corona beautiful can alter the technology around a planet. The sun's 11-year cycle also changes its ultraviolet output. The total energy change is modest, yet the upper atmosphere responds to those wavelengths, and the distribution of particles and magnetic fields changes more substantially. Space weather is therefore about spectrum and structure, not only total brightness. No single index captures the whole cycle. Sunspot counts, flare classes, magnetic maps, and solar wind measurements describe different aspects. Scientists combine them into a picture that is always provisional, updated as new observations arrive. The cycle links deep rotation to distant auroras. To understand that link, we need a way to hear the interior without opening it. Sunspot latitude adds another clue. New spots tend to appear at higher latitudes after a minimum and then migrate toward the equator as the cycle advances. A diagram of those positions produces the butterfly pattern. It is a record of where magnetic flux emerges, not a picture of birds or wings, and it gives Dynamo models a demanding shape to explain. The polar fields matter as well. They are weak compared with a concentrated sunspot, but they help set the large-scale magnetic structure of the next cycle. When the polar field reverses, the change can be followed in magnetograms and in the distribution of coronal holes. The cycle is global, even though its most visible features are local. Because activity is distributed, space weather forecasts use probabilities. A magnetic map can show that an active region is capable of a flare, but it cannot specify the exact minute of release. Forecasting is therefore a measured assessment of conditions, not a promise that every bright region will erupt. The next problem is evidence. The sun cannot be opened, and light from the core is transformed before it reaches the surface. Helioseismology offers another route. It measures tiny oscillations on the photosphere and uses their travel times to infer the layers below. The sun rings in many modes. Pressure waves move through the plasma, reflect from changing conditions, and interfere to make patterns at the surface. Some modes sample shallow layers. Others travel deeper, allowing scientists to combine thousands of frequencies into an interior map. A wave moving through hotter, denser material changes speed. Rotation also shifts the frequencies. By comparing waves traveling in different directions, researchers measure how quickly various depths rotate and identify flows beneath the photosphere. Helioseismology helped establish the depth of the Convection Zone and the location of the Tachocline, the shear layer where rotation changes rapidly. It also reveals currents that carry magnetic flux and patterns that recur with the solar cycle. The method resembles listening to an instrument, but the sun is not a hollow bell. Its entire volume participates. The sound waves are pressure disturbances in plasma, and the surface motions are tiny compared with the disk's 696,000 kilometer radius. Computers compare observed oscillations with models of temperature, density, and composition. A model that predicts the wrong travel times is adjusted. In this way, the interior is reconstructed through repeated agreement and disagreement, not through a single photograph. The waves do not show every detail. Turbulence, magnetic fields, and limited viewing angles blur the answer. Yet helioseismology narrows the possibilities enough to test theories of transport and dynamos. The sun's hidden layers are therefore not inaccessible in the absolute sense. They are inaccessible to a drill, but open to a conversation among waves, particles, and light. The waves also reveal that the surface is never perfectly still. Granules rise and fade, active regions rotate across the disk, and global modes continue beneath them. Instruments average over these motions, then separate the patterns by frequency and direction. The resulting data set is less like a single recording and more like a library of overlapping voices. A model earns trust when it explains several voices at once. It must match the measured radius, the luminosity, the surface composition, the oscillation frequencies, and the neutrino flux. A change that fixes one disagreement can create another. The interior is constrained by this web of tests, which is why small differences between models remain scientifically useful. Helioseismology also tracks flows that transport angular momentum. Those flows may help explain why the 11-year magnetic cycle has its observed timing and latitude pattern. The data do not turn the dynamo into a solved machine, but they show where its moving parts must be located. The first problem is knowing what the sun contains when no sample can be brought home. Spectroscopy answers part of it. Elements absorb and emit particular wavelengths, and those patterns remain recognizable even after the light has crossed space. Hydrogen and helium dominate the spectrum, while narrower lines reveal oxygen, iron, calcium, sodium, and other elements. An absorption line forms when cooler gas in front of a hotter source removes a precise range of wavelengths. The depth and shape of the line depend on temperature, density, abundance, and motion. A line is not a simple label. It is a small equation written across the spectrum. The Doppler effect adds movement to composition. A line shifted toward shorter wavelengths shows motion toward the observer. A shift toward longer wavelengths shows motion away. Across the disk, those shifts reveal rotation, convection, oscillations, and the rise of active regions. Helioseismology supplies the interior's density profile, while spectroscopy supplies the atmosphere's chemistry. Neutrinos provide a third measurement. Because they are produced in the fusion chain and interact weakly, their number and energy distribution test the model of the core more directly than surface light can. The early solar neutrino problem showed why independent messengers matter. Detectors found fewer electron neutrinos than expected. The resolution was not that fusion had stopped. Neutrinos change flavor as they move, so a detector built for one flavor misses some of the original stream. The sun's composition is not perfectly uniform. Fusion has altered the central hydrogen and helium balance, and convection has mixed much of the outer envelope. The boundary between those behaviors leaves a chemical and dynamical record that models must reproduce together. When scientists say the sun is mostly hydrogen and helium, they are describing both its ingredients and its history. Hydrogen is the starting fuel. Helium is the product accumulating at depth. The heavier elements are a small fraction, yet they influence opacity and therefore the way energy moves. Light, sound, and neutrinos do not tell identical stories. Their agreement is what makes the interior model persuasive. The star is known by the way its different messengers meet at the same answer. Spectroscopy has limits that are as informative as its successes. The visible spectrum samples layers where photons can escape, while the deeper composition is inferred through models of mixing and opacity. A line can be weakened by ionization, even when an element is present, and a turbulent atmosphere can broaden a line without changing the abundance. Scientists therefore compare many lines and many wavelengths rather than trusting one vivid feature. Neutrinos add a check that does not depend on the photosphere. Their energies correspond to reactions in the core, and their arrival rate responds to the temperature and composition there. A small change in the modeled core can alter the predicted flux, allowing detectors on Earth to test conditions deep below the visible surface. The three evidence streams meet in a layered model that is continually revised. The model is not a map drawn once and filed away. New observations alter the opacity tables, the treatment of convection, or the assumptions about composition. The Sun remains the nearest laboratory for stellar physics because it offers enough detail to expose every approximation. The next layer of the story is motion. The Sun does not rotate as one solid object. Its equator turns faster than its poles, and the rate also changes with depth. This differential rotation stretches magnetic fields that convection has carried through the surface. The Tachocline is a narrow shear region near the base of the convection zone. Above it, the plasma rotates differentially. Below it, the radiative interior rotates more nearly as a solid body. The contrast stores and organizes magnetic energy, although the exact dynamo mechanism remains an active field of study. Convection twists the field further. Rising and sinking plasma move across lines of magnetic force, while rotation turns those motions into large-scale patterns. The combined process is called the dynamo, mechanical motion maintaining and amplifying magnetic fields. The magnetic field emerges in bundles. Some bundles rise as flux tubes, carrying strong fields through the convection zone. When they break through the photosphere, they create paired sunspots with opposite polarity. The pair is a surface clue to a structure that began far below. As the cycle proceeds, the polarity of the global field reverses. The 11-year sunspot rhythm is therefore one half of a roughly 22-year magnetic cycle. The reversal is not a single switch. It is a gradual rearrangement across many active regions and the polar field. The dynamo is not visible directly. Its evidence appears as field maps, sunspot latitudes, coronal shapes, and the timing of flares. Helioseismic flows add another constraint, showing how currents beneath the surface migrate as the cycle develops. Differential rotation also changes the path of an individual feature. A spot near the equator can move across the disk faster than one at a higher latitude. The visible surface becomes a clock, a map, and a record of forces acting below it. The magnetic dynamo connects the deepest accessible measurements to the highest corona. To see its effects from Earth, we follow the light that leaves the photosphere and crosses the space between planets. The shear is not confined to a neat horizontal sheet. Plumes rise through the convection zone, and large-scale flows carry magnetic flux toward the poles and back toward lower latitudes. Some of these motions are inferred from surface tracking, Others emerge only after the oscillation data are combined with long-term magnetic maps. Magnetic energy can be stored quietly for a long time. A field line does not need to flare simply because it is strong. It must also be arranged so that a small displacement can produce a new, lower energy configuration. The waiting period is part of the physics. It gives the convection zone time to twist and concentrate the field before an event. The dynamo is therefore a cycle of construction and release. Differential rotation builds large-scale field. Convection carries it through the surface, and reconnection rearranges it in the atmosphere. The cycle leaves traces at every height, from subsurface flows to coronal streamers. The first anchor number is 8 minutes and 20 seconds. That is approximately how long light takes to cross the 150 million kilometers between the Sun and Earth. The interval starts when a photon finally escapes the photosphere, not when the fusion event that supplied its energy occurred. At the photosphere, the escaping radiation includes visible light, infrared, ultraviolet, and smaller amounts of higher energy wavelengths. Earth's atmosphere absorbs much of the ultraviolet and nearly all X-rays, while visible light reaches the ground through a broad atmospheric window. The light spreads as it travels. Its energy is distributed over a sphere that grows with distance, so the intensity at Earth is far lower than near the Sun. The planet receives only a fraction of the total output, yet that fraction drives climate, weather, photosynthesis, and the visible daytime sky. Photons entering the atmosphere scatter from molecules. Blue wavelengths scatter more efficiently than red wavelengths, which is why the sky appears blue when the sun is high. At sunrise and sunset, the longer path through air removes more blue light and leaves warmer colors. Clouds reflect and absorb part of the incoming radiation. Snow, ice, soil, and ocean each return different fractions to space. The sun spectrum is therefore transformed twice, first by the solar atmosphere, then by the Earth's atmosphere and surface. The time delay is short for weather, but real for observation. A solar flare seen on a monitor has already happened more than 8 minutes earlier. A warning system cannot remove that delay, only use the signal to prepare for slower particles and plasma that may follow. Neutrinos share the same final travel time to Earth, but they left the core directly. Their arrival is a present tense sample of fusion, while visible sunlight is a delayed and processed sample of energy that began its outward route long before. The sun's light is therefore both immediate and ancient. It warms a face, powers a leaf, and illuminates a room, yet the energy passed through layers that erased the identity of its first photon. The spectrum also carries the sun's rotation. One edge of the disk moves toward the observer, while the opposite edge moves away, shifting the same absorption lines in opposite directions. Measuring that split gives a rotation rate independent of watching a sunspot cross the disk. The light contains the movement of the source inside its wavelength pattern. Solar irradiance varies slightly as active regions cross the visible hemisphere. Dark spots remove some light, while bright faculae add light around them. The total change is small compared with the steady output, yet precise instruments can separate these variations from changes produced by Earth's own atmosphere. At the ground, sunlight is shaped again by elevation, humidity, dust, and cloud. A blue noon sky and a red horizon are different paths through the same spectrum. The sun sends a broad range of wavelengths. The planet chooses which ones reach a particular observer. The next question is where the sun's atmosphere ends relative to Earth. The answer is that Earth orbits inside the heliosphere, a magnetic bubble inflated by the solar wind. The planet is not inside the corona, but it remains inside the sun's extended plasma environment. Earth's magnetic field creates a protective cavity called the magnosphere. Incoming solar wind particles are deflected around it, while field reconnection opens temporary channels. The shape changes with the wind speed and magnetic direction, compressed on the day side and stretched into a long night side tail. Near the poles, particles guided down magnetic field lines collide with upper atmosphere gases. Oxygen and nitrogen emit colored light as they return to lower energy states. The aurora is a spectral response to a magnetic connection between Sun and Earth. The solar wind also presses on the ionosphere, a region of charged particles high above the surface. Radio signals can refract, scatter, or be absorbed differently as the ionosphere changes. Navigation systems and communication therefore carry a subtle signature of solar activity. Coronal mass ejections can strengthen these effects. Their magnetic fields may reconnect with Earth's field and drive currents through the magnetosphere. The resulting geomagnetic storm is a system response, not a direct transfer of the entire CME into the ground. The atmosphere also receives ordinary sunlight. Ultraviolet radiation breaks molecules apart and warms the stratosphere. Visible light warms land and ocean. Infrared radiation leaves the surface and is absorbed and re-emitted by gases. The same star supplies both the steady background and the variable disturbances. From the ground, the sun appears to rise and set because Earth rotates. From the sun's perspective, Earth is one moving point among planets, embedded in a wind whose density and field change continuously. The familiar sky hides a larger environment. Every layer inside the sun contributes to this connection. Core fusion supplies energy. Convection shapes fields. The corona releases particles. Earth's magnetosphere receives the result. Earth's atmosphere is not a passive screen. Ultraviolet light changes its chemistry, while charged particles follow magnetic paths that vary with altitude. The upper atmosphere expands and contracts as energy arrives, changing the density that satellites encounter. Even a quiet solar day is a negotiation among radiation, particles, and fields. The magnetosphere also sends information back through its response. Ground magnetometers record changing currents. Auroral cameras trace where particles enter. Radio instruments detect how the ionosphere bends signals. A storm is reconstructed from many modest measurements, each one describing a different part of the planetary system. Other planets provide comparisons. Mars has no global magnetic field like Earth's and has a much thinner atmosphere, while Jupiter's powerful field creates a large magnetosphere of its own. The same solar wind produces different results because each planet supplies a different shield and atmosphere. The first anchor number is 4.6 billion years. The sun formed about that long ago from a collapsing cloud of gas and dust. Gravity gathered most of the available material into the central protostar, while a rotating disk around it supplied the raw ingredients for planets, asteroids, and comets. As the protostar contracted, gravitational energy became heat. The center grew denser and hotter until hydrogen fusion began. That ignition did not resemble a flame turning on. It was a gradual transition in which pressure from fusion helped halt the contraction and establish a long-lived balance. The young sun was more active than today's quiet average. Its magnetic field was strong, and its wind was likely more powerful. The early planets formed inside that changing environment, while leftover debris collided, melted, and settled into the architecture we recognize. More than 99% of the solar system's original available mass ended in the sun. The planets are important to us, but they are a thin arrangement around a star that contains nearly all the material. The sun's age is recorded in meteorites, stellar models, and the composition of ancient rocks. Different methods converge on the same broad timescale. The star has been stable long enough for oceans, continents, and life to develop on one orbiting world. Fusion has not consumed the sun uniformly. The central region has accumulated helium, while the outer convection zone remains mixed by motion. This internal history changes the pressure profile and slowly increases the sun's luminosity. At present, the sun is roughly halfway through the stable hydrogen burning stage of its life. The phrase halfway is a model-based estimate, not a countdown displayed on the surface. Its future depends on how the core contracts and how the surrounding layers respond. The star's current appearance is therefore a moment in a much longer sequence. The same layers that seem permanent are slowly changing, one reaction and one circulation at a time. The protoplanetary disk also explains why the planets orbit in a broad plane. Material inherited the cloud's rotation, and collisions within the disk damped many random motions. The sun gathered the central share, while the remaining grains became worlds, moons, and smaller bodies. The architecture around the star is a fossil of its birth conditions. Early magnetic activity left traces in meteorites. Tiny grains record the direction of ancient fields, while isotopes reveal the timing of irradiation and heating. These clues are indirect, yet they connect laboratory samples to a young sun that no human eye observed. The present sun is quiet enough for stable climates over long intervals, but it is not static. Its luminosity, rotation, composition, and magnetic field all change. Stability means that the changes remain within a range that allows the star to persist, not that every property is fixed. The next question is what happens when central hydrogen becomes scarce. In roughly another 5 billion years, the core will no longer sustain the present balance. Hydrogen fusion will continue in a shell around a helium-rich core, while the core contracts and heats. The outer layers will expand dramatically. The sun will enter a red giant phase, becoming much larger and cooler at its visible surface even as the interior grows hotter. The photosphere will move outward, and the familiar boundary between solar atmosphere and planetary space will be redrawn. The inner planets will face intense heat, and Earth's ultimate outcome depends on orbital evolution and the changing solar envelope. The details are modeled rather than observed directly, so the broad sequence is secure while the exact distances and timings remain conditional. Eventually, the sun will shed its outer layers. The expelled gas will form a planetary nebula, illuminated by the hot remnant at its center. The name refers to historical appearance, not to a connection with planet formation. The remnant will be a white dwarf, roughly Earth-sized but containing a large fraction of the sun's mass. It will no longer generate energy through ordinary hydrogen fusion. It will cool gradually, radiating stored heat into space. The layered model changes again. A white dwarf has a dense interior supported by electron degeneracy pressure, a thin atmosphere, and no active convection zone like the present sun. The star's history remains visible in its composition and cooling rate. No human observer will watch the entire sequence. The timescale is longer than civilization, longer than recorded history, and comparable to the age already behind us. Yet the physics is present in other stars at different stages. letting astronomers compare the sun's future with a population of stellar examples. The sun's future is not a sudden ending. It is another change in transport. Fusion moves from the core to a shell. Convection expands. The atmosphere is lost, and a cooling remnant remains. The red giant phase will expose how closely the layers depend on one another. A contracting core raises the temperature of the shell around it. The shell adds energy to the envelope, and the envelope expands until its outer density is extremely low. The visible surface cools even as the central regions become more intense. When the outer envelope is lost, the material returns elements to space. Carbon, nitrogen, and other products made inside the star become part of the chemical history of the galaxy. The sun's end is also a contribution to later clouds and future generations of stars. The white dwarf remnant will be small because gravity compresses it after the envelope is gone. Electron degeneracy pressure resists further collapse without requiring active fusion. Over immense time, the remnant simply cools. A star that once held the planets in its wind becomes a faint, dense ember moving through the galaxy. We have talked about the core, where a temperature of about 15 million degrees Celsius lets hydrogen nuclei combine into helium. We have talked about density near 150 grams per cubic centimeter, pressure held against gravity, and neutrinos that leave the fusion region almost immediately. We have talked about the radiative zone, where energy moves by repeated interactions, and NASA estimates roughly 170,000 years for the outward passage. We've talked about opacity, changing wavelengths, and the way a photon loses its original identity while its energy continues outward. We have talked about the convection zone, where hot plasma rises and cooler plasma sinks. We have talked about granules, the photosphere at about 5,500 degrees Celsius, and the optical depth that creates a surface without a solid shell. We have talked about sunspots and the approximately 11-year cycle. We have talked about magnetic reconnection, flares, prominences, and the chromosphere rising from roughly 4,000 to 8,000 Kelvin. We have talked about the transition region, only about 100 kilometers thick in the simplest description, where temperature rises toward hundreds of thousands of Kelvin. We have talked about the corona, reaching roughly 2 million degrees Celsius, even though it is far thinner than the photosphere below. We have talked about coronal holes, streamers, the solar wind, and the heliosphere, the magnetic bubble that carries the sun's influence beyond the planets. We have talked about Parker Solar Probe, which passed about 3.8 million miles above the surface on December 24, 2024. We have talked about helioseismology, spectroscopy, and neutrinos. We have talked about rotation, the Tachocline, and the dynamo that turns fluid motion into magnetic cycles. We have talked about light taking about 8 minutes and 20 seconds to reach Earth after it escapes the photosphere. We have talked about a star formed about 4.6 billion years ago, holding more than 99% of the solar system's original available mass, with roughly another 5 billion years before its red giant phase. We have also talked about the meaning of a boundary. The core boundary is a change in fusion rate. The radiative boundary is a change in stability. The convective boundary is a change in the way matter carries energy. The photosphere is a change in transparency. None of these boundaries is a wall, yet each one changes what the plasma can do. The layers overlap in time. A photon may spend a very long interval in the radiative zone, while a sound wave crosses the same region on a much shorter schedule. A magnetic field can connect the photosphere to the corona in one structure, even as convection reshapes its footpoints below. The sun is not a stack of independent rooms. It is a set of processes occupying the same sphere. The core tells us why the star shines. Its density and temperature allow the proton-proton chain, and the pressure generated by hot plasma balances the inward pull of gravity. The rate is slow enough for a lifetime measured in billions of years. A more massive or more compressed star would burn differently, but the sun's particular balance gives Earth a long, steady source. The radiative zone tells us why the output is steady. Energy does not race from one fusion event to the surface. It is absorbed, re-emitted, scattered, and redistributed. The delay smooths local changes. By the time radiation reaches the photosphere, it represents the combined work of a vast volume rather than a single reaction. The convection zone tells us why the surface moves. Hot parcels rise, cool parcels sink, and the pattern breaks into cells that become granules near the optical boundary. Convection also carries magnetic fields. The same motion that transports heat helps build the structures that later release energy in flares and coronal mass ejections. The atmosphere tells us why the visible disk is not the whole sun. The chromosphere and transition region are thin but dynamic. The corona is thin but hot. The solar wind carries fields and particles beyond the planets. What looks like a bright circle is therefore the center of a much larger environment. The evidence is layered too. Spectral lines sample the atmosphere. Oscillations sample the interior. Neutrinos sample the fusion region. Spacecraft sample the wind. Each method has blind spots, and each method corrects the others. The picture becomes reliable because the independent routes converge. The title can now be answered without a metaphor. Inside the sun is hydrogen and helium plasma in a gravitationally confined state, changing from a fusion-dominated core to radiation-dominated and convection-dominated regions, then to a magnetic atmosphere that flows outward. The layers are physical conditions, and their transitions are the story. The title asks what is inside the sun. The honest answer is not a single substance or a hidden chamber. Inside the sun is a sequence of conditions: fusion in the core, radiation through a deep interior, convection beneath an optical surface, and magnetic plasma extending into space. The sun has no solid inside to stand on. There is no floor beneath the photosphere, no shell separating one chamber from the next, and no empty center waiting to be reached. There is only plasma shaped by gravity, pressure, temperature, radiation, and magnetic fields. Layer by layer, the changes are real even when the borders are models. The core is defined by fusion. The radiative zone is defined by the way energy diffuses. The convection zone is defined by overturning motion. The photosphere is defined by optical depth. The chromosphere, transition region, and corona are defined by temperature, density, and magnetic behavior. So what is inside the sun? A furnace, if furnace means nuclear fusion held by gravity. An ocean, if ocean means fluid motion without a solid bed. An atmosphere, if atmosphere can be charged, thin, and threaded by fields. None of these metaphors is complete, but together they point toward the physical answer. The star above a morning street is also the source of the warmth on a window, the energy in a leaf, and the pressure that drives a weather system. The photons arriving now began as energy released in a core hidden beneath 696,000 kilometers of plasma. Tonight, we're going to look at the most familiar star in the universe from the inside out. The sentence returns with a different weight. The familiar star is not familiar because it is simple. It is familiar because its light has accompanied every human day, while its interior remains a layered world of equations, waves, and changing fields. From a distance, a star invites a single word: sun. Up close in thought, it opens into a vocabulary of gradients and flows. Temperature rises and falls. Density thickens and thins. Radiation changes direction. Plasma moves in cells, loops, jets, and winds. The vocabulary is technical, but the pattern is coherent. Each condition prepares the next. The core does not send a finished beam through a tunnel. It supplies energy to a medium that transforms it. The radiative zone delays and redistributes that energy. The convection zone gathers it into moving parcels. The photosphere releases it at the depth where the medium becomes transparent. Above that, magnetic fields shape a tenuous atmosphere whose heat and particles continue outward. This arrangement is why a visible surface can coexist with an invisible interior. The edge we see is an optical decision made by matter. A different instrument would choose a different height. Hydrogen alpha reveals the chromosphere. Extreme ultraviolet reveals hot coronal loops. X-rays reveal still hotter regions. The sun has many surfaces, each one a window onto a different process. The same arrangement explains why the sun can seem steady and changeable at once. Its total light varies only modestly across a cycle, while individual magnetic regions flare, fade, and rotate away. Its core changes over billions of years, while a granule rises and disappears in minutes. Stability and motion occupy the same star at different scales. Earth receives the integrated result. The quiet warmth of a wall, the green chemistry of a leaf, and the colors of an aurora are separated by distance and by mechanism, but their history passes through the sun. A photon, a charged particle, or a magnetic disturbance can begin in a different layer and end in a different part of the planetary system. The sun's scale also changes the meaning of time. 8 minutes and 20 seconds is the final crossing to Earth. About 170,000 years describes a diffusive passage through the radiative zone. 11 years describes a magnetic rhythm. 5 billion years describes a future phase. Several clocks run inside one sphere, and none of them cancels the others. There is no single view that contains the whole star. A cutaway diagram is a model. A telescope image is a selected wavelength. A helioseismic map is an inference from waves. A neutrino count is a statistical message from the core. The picture becomes richer when these partial views are placed together, layer over layer, process beside process. The familiar disk is therefore a beginning rather than a conclusion. It is the place where hidden energy becomes visible, where the star's interior meets an observer, and where a changing magnetic field leaves marks that can cross the dark between worlds. The core is hidden, but not silent. Neutrinos pass through it. Pressure waves carry its imprint. The temperature and density leave consequences in every layer above. A star can conceal its center while continually announcing that center through measurable effects. The radiative zone is slow, but not inert. Its photons change direction thousands of times. Its opacity depends on composition. Its temperature gradient decides whether radiation can carry the next increment of energy. A broad region can be quiet in appearance and still determine the star's brightness. The convection zone is visible in fragments. A granule is small compared with the sun, yet each granule is part of a circulation that reaches deep below the photosphere. The pattern resembles a woven surface because the motions overlap, merge, and disappear. Heat becomes texture. The photosphere is the threshold of ordinary sight. It is where the optical depth approaches one, where photons begin to escape freely, and where the disk acquires its apparent edge. The edge is sharp because transparency changes rapidly, not because matter ends abruptly. The chromosphere and corona extend the story upward. Hydrogen lines reveal jets and filaments. Ultraviolet light reveals loops. X-rays reveal hot magnetic structures. An eclipse briefly makes the atmosphere visible to unaided eyes, but instruments can watch it every day. The solar wind carries that atmosphere outward. It bends magnetic fields into a spiral, inflates the heliosphere, and meets every planet with a different combination of shield and atmosphere. Earth answers with auroras, currents, and radio changes. The answer is local, but the source is stellar. The sun is therefore both near and unreachable. Its light crosses the distance in minutes, while its interior can take ages to reveal itself. The most familiar object in the sky remains a layered problem, made legible by patient observation. To name the layers is to name the routes by which the star remains in balance. Gravity draws inward. Pressure pushes outward. Radiation diffuses. Convection circulates. Magnetic fields store and release energy. The balance is not a frozen equation. It is a sequence of small adjustments that add up to a stable star. Every observation carries a trace of that balance. A dark sunspot records suppressed convection. A spectral line records an ion and its motion. A neutrino records a reaction in the core. An aurora records a field arriving from the solar wind. These traces are separated by distance and by time, yet they belong to one connected system. The answer to the title is therefore physical and unfinished. Inside the sun is matter under conditions that Earth cannot reproduce for long, moving through layers whose borders emerge from equations and observations. The star is familiar at a glance and inexhaustible at depth. Its light leaves a surface that is not a shell, travels through a heliosphere that is not empty, and arrives at a world that is not separate. The same star continues through every layer of the journey, from the center of the sphere to the edge of human attention. What begins as pressure and fusion becomes radiation, motion, magnetism, and a quiet blue day. The chain is continuous even when the names change. The sun remains one body, one history, and one source moving through many forms. The final view is simple, only because the layers are working together. Beneath the calm disk, every depth is carrying energy, answering gravity or recording the next change. That work continues without an audience, whether the sky is bright or hidden by cloud, whether the disk is quiet or crossed by a flare. The layered star is always in motion. Its changes are gradual, connected, and measurable. The same motion continues through every depth. It carries the story outward, from the core to the corona, from the corona to Earth. One continuous star, measured in many voices, seen across changing layers, held together by gravity, always. One layer, then another. Hydrogen becoming helium, energy changing hands, light finding a way out, magnetic fields reaching into the dark, and a planet turning beneath the result. The sun is 1.39 million kilometers across, yet its influence is larger than its visible disk. Its wind fills a heliosphere. Its light crosses space. Its interior changes slowly enough to seem eternal and steadily enough to shape a future. The question has an answer, but the answer remains in motion. Inside the sun is not a thing. It is a process, continuing now beneath the daylight. Good night.